morning. I want to welcome you to today's edition of our Sharpen Your Dairy Skills While We Flatten the Curve webinar series. I'm really pleased to again welcome back Dr. Dana Kirk, who's a faculty member in the Department of Biosystems and Ag Engineering at Michigan State. Dr. Kirk currently focuses largely on anaerobic digestion. He's in charge of the program focused on that at Michigan State, and a lot of his teaching and outreach efforts are in that space. But he has broad expertise in waste management. He spent time working in industry on equipment design and on permitting work around just overall nutrient management plans and handling manure. And so brings a great deal of expertise and a lot of applied sort of experience to this. So thanks, Dana, for being a part of this again.
Well, thank you for participating today. I'm going to talk to you about manure treatment technologies, kind of what the state of the art is, and I guess walk through at least my perspective on how I look at and think about manure treatment when I talk with dairy farmers. So quick background. I sit in biosystems and agricultural engineering at Michigan State. My primary role is to manage the Anaerobic Digestion Research and Education Center, oversee our South Campus digester. And both of those come with, extensive extension and outreach and research components as well. So varied role, but very much focused on kind of waste management, primarily organic waste management around livestock and food processors a lot of times. So a little bit about me and the program that I represent. So as we're all aware, the dairy industry is a very dynamic industry, even outside of pandemic times like we're in now. It's been a very active and changing industry over the years. We've seen significant improvements, of course, in milk production, efficient use of resources, environmental impacts. But the dairy industry here in Michigan and across the country has been challenged. I mean, there's concerns about nutrient management, land application of manures, the impacts on air quality, water quality, ground fertility, concerns about nutrient density, odors, and emissions around the farms themselves. And this goes across all animal agriculture, so it's not just dairy specific, but we're looking at it from a dairy standpoint today. Manure transfer and application, again, that's the season we're in here in Michigan. Farmers are out applying manure, and so there's more truck traffic on the roads. We're hauling out of campus right now, and so we've got trucks leaving to go on the fields every day. So you got concerns with transportation and truck traffic and potential damage to roads, and then making sure we get applications done on appropriate conditions and outside of inclement weather. So the dairy industry is also at a critical juncture. Where the current state is, we're seeing increasing regulations and pressure from society about how we manage manure. Concerns about litigation. We've seen litigation on dairies in the western states over how manure is stored and land applied, and in comparing manure to hazardous wastes and regulated waste. And so there's pressures around that. Surface and groundwater issues related to how we use fertilizer, particularly nitrogen and phosphorus. Agriculture is part of that concern. Manure management is part of that concern, but synthetic fertilizer, commercial fertilizer is also part of that. And then making sure we maintain consumer trust. So making sure the consumer understands that the dairy industry is focused on good animal care practices, good environmental practices, and providing cost-effective, nutritious food products for them. Where we'd like to be, and this is taken from the Innovation Center and Nutrient, we would like to resolve these societal issues related to water pollution and greenhouse gas emissions. So we'd like to get us into a state where, society realizes that we are good actors and good neighbors, and that we're doing everything in the best interest of maintaining good environmental conditions. We'd like to see some economic benefits, of course, because to come into improved conditions costs money to modify how we manage manure, modify how we process and land apply and utilize the nutrients that are produced. And so we'd like to see, some recognition and some economic benefit to that. Now we are seeing some of that related to carbon management, carbon emissions when we talk anaerobic digestion. But when it comes to nitrogen and phosphorus, it's hard to monetize some of the things that we might do to improve how we get those nutrients back into the field condition and the field system. And then we want to make sure that, again, society really has an understanding that we are, as a dairy industry, and working in the best interest of our animals and our consumers, and providing the best conditions for all of the products that we generate. It's interesting, and I pulled this up, and I wasn't going to put the slide in, but I looked at it again this morning, and I thought this is kind of an interesting depiction. This is from a few years ago, and it's very much focused on a Michigan-centric topic, Michigan or Great Lakes region topic, Lake Erie, and some of the issues associated with Lake Erie. And I thought it was interesting how when they look at and report about phosphorus inputs, the left side of the chart, that manure is separated from farm fertilizers. But then when we look at in the delivery section, we roll manures and farm fertilizers into one topic area. Everything else remains in its own separate buckets. But when we look at it on the delivery and kind of the runoff side of it, we seem to lump those together. And I'm not sure that really is an accurate depiction and gives us a really good understanding of what is the manure, the influence of manure on this versus the farm fertilizer side of it. And so I just thought that was interesting and something to think about, that, how we impact manure or how we manage manure changes this phosphorus input. It may not change the overall amount, but again, as we look at manure treatment, the idea is that we want to reduce the contribution of phosphorus leaving the fields through some sort of runoff action. And so I guess I would like to see, as we move forward, as an industry, we push to keep those topics separate, because they are very separate. And manure is different than farm fertilizers because manure comes with carbon, and carbon acts a bit like a glue in the soil, and carbon also has other positive benefits in the soil. When we look at it again from a very focused kind of Michigan standpoint, we're under a new EGLE, or Environment, Great Lakes and Energy Department CAFO permit. So this is our new NPDES permit. It's just taking effect as of this month, I guess, or as of April. Interesting treatment in there in the new permit is largely undefined. And so there's no push or requirement for treatment as a regulated or permitted farm. There is a focus, of course, on storage. And so storage is extremely important. And we need to have all those properly designed and engineered storages, but we also have to have sufficient volume to get through the winter months for storage. And so the 6-month storage requirement is very much allowed and brought forth in that. Anaerobic digestion is really the only thing that's defined in the treatment section of the permit. And it really is defined for the sole purpose of bringing outside feedstocks onto a farm. So if I were bringing food processor waste or some other non-manure product onto the farm, a lot of the language in that treatment section is around that. And it's very consistent with prior permits. So the treatment section really is largely unchanged from the prior permit. The one thing to keep in mind, though, as we think about manure treatment and processing our manure and maybe separating or differentiating nutrient types and solid types, is it is still defined as a CAFO waste. And so products or effluents of treatment systems are still defined as CAFO waste, and therefore they're still beholden to all of these storage requirements of the permit. And so, we still have to comply with NRCS 313 practice standards on how we design and operate our storages. We still have to have sufficient volume of the storages for the products that would come out of a treatment system, and we have to be able to hold those for up to 6 months. And so even though we may invest and go quite a ways into the treatment process, the language there still says that all of our products out of that effluent system or treatment system are going to be regulated as CAFO waste. And so if you do a treatment system that goes beyond maybe just basic solid liquid separation, there may be need to enter into an individual permit so that you can get some site-specific definition of how you would manage the effluents from a treatment system. But it is there to keep in mind that, again, we have to have storage capacity for all of our manure type products. When we look at nutrient recovery categories, it's very much a system approach, and it's kind of just a stepwise approach that we have coarse and fine separation solids, we've got membranes, we've got anaerobic digestion and other energy generation concepts that we talked about a little bit last week. We've got fiber drying, and we've got bedding recovery systems. So again, if we're looking just simply for bedding products, that's there. And there's other technologies that are coming, coming out all the time. So there's odor control technologies. There's other manure treatment practices that are potentially available and being developed constantly. As we start to think at the farm side about manure treatment, nutrient recovery, there's several factors that producers need to consider very early on in the process. And it's probably even before any significant conversations with equipment or technology vendors or equipment providers, because you want to make sure that you have conversations that line up what you're looking for and then allow you to talk and communicate effectively with people that are selling the equipment. So think about, what is the management style of your farm? How is it sand bedding? Is it scrape? Is it flush? Is it 3 times a day collection, or are you scraping 2x when you're milking? And are you willing to modify? Are you willing to change beddings if necessary? So think about what the management style is, where the points are that you have some flexibility and some willingness to change your practices, because that sets the tone for kind of how you look at and start to think about a system. Think about, what is the cost of your management today? So from storage or from the barn to the field, what is the cost of your manure management system? And are there tweaks that you can make, small tweaks to that manure management system that allow you to better manage your manure, but not, require significant infrastructure or change to how you manage manure? So get a good handle, because a lot of farms, when I talk to them, don't have a good understanding of what it costs to land apply manure, let alone collect, store, and land apply manure. Think about the needs and the wants and really separate those out and say, okay, this is what I need for my dairy to be the best that it can be from a manure management standpoint. And be in compliance and be a good neighbor and be a good actor. This is what I really need to do. And then the wants, this is what I'd love to do. If we weren't facing low milk prices and kind of an instability in the industry and a lot of uncertainty, in the near future, what are the things you want to come out of the system? But there is a difference between what you need and what you want. And so you need to have those separated out and put those into buckets, because they should be weighted differently when you think about manure management. And then pull out the crystal ball, and you have to think about this. What does your farm look like in 10 years? Are you growing? Are you just going to stay where you're at and you're comfortable and the farm is what it is and you're at the top of your permit? You've got a lot of other factors around you that aren't going to allow you to grow. Or are there significant expansion plans in the works? Are you looking at anaerobic digestion? Are you looking at changing how you dairy? So think about, what is this farm going to look like in 10 years? Because it impacts where you might put equipment. It impacts what kind of equipment you may want to get. It impacts, how you lay the equipment out, because maybe there's room to expand the equipment down the road, and it's cheaper to build a building a little bit larger today than it is to go back and build a second building 5 years from now. And so have that conversation, amongst your management, and think about, what does this farm look like in 10 years? And then think about what is going to be required in 10 years. And I just had this conversation last week with a dairyman from Utah about, if I do these things with my manure system and I install a digester to collect biogas and, make renewable natural gas and all of that, what's that mean if a carbon tax comes down the pipe in 5 years? In what potential regulatory changes could we face, or what changes could our cooperative require or our consumer require? And again, it's very speculative, but at least it just adds value and it adds depth to how you look at and think about manure management and expanding that manure management or changing how you manage manure. And so ask these questions, think about it, because it starts to probe and it will help you develop what ideally is a better system for your style, for your long-term goals. And that sets you on a path of kind of being super, very successful in the next 10 years. These are long-term investments. I mean, some of this equipment wears out, 5 to 10 years down the road, but a lot of this equipment could still be operating very well 15 years, 20 years after it's installed. And so have a little bit of a long-term, long game perspective on it. And it's best to think about what that long game looks like early on. Make sure you've got a good handle on your manure handling system, collection, conveyance, sand separation, or any treatment systems that may be installed, all impact what the manure looks like in the manure characteristics. And that all impacts how you look at installing and developing a new manure separation system, manure handling system, manure treatment system, nutrient partitioning. Those are all terms that kind of get tossed into the bucket when we talk about this. So, anytime we talk manure management and changing manure management, we've got to understand our characteristics. We've got to have a discussion about the bedding practices and the bedding that we use. We have to think about handling, and we got to think about what the products are. What do we want to come out of this? So again, it's what do we need to come out of this, but what do we want to come out of this? And think about what those products are, and is there a need? Do I need just a high carbon material that I can move off, and I've got crop growers nearby that are just looking for carbon in the soil. That's one type of system that may be differentiated from somebody that wants a high phosphorus fertilizer or somebody that wants an ammonia product. So think about what those products are, and you kind of have to run the scenarios backwards and forwards a couple of times and think about it in a system so that you can best invest the money wisely. Manure characteristics change. This is the one thing that we often know, but we don't remember or think about. There's an as excreted range when it comes to total solids. We add bedding, we add water, we do sand separation. So there's a continuum, of close to pure water to very stackable dry manure that we work with in the industry. And so, we need to think about what those characteristics are, how they affect how we collect and handle manure, and factor all these in and make sure we communicate that out with people that are guiding us and helping us think about these manure treatment systems. So manure treatment, nutrient recovery, nutrient partitioning, you can throw a lot of words in there. There are a lot of technologies that are in this bucket or in this topic area. Solid liquid separation using screw press separators. It's been done thousands of times in the US. Pretty well known, pretty well understood. Anaerobic digestion, you've got several hundred examples across the US on farms, relatively commercially viable. Technology and how it fits into a farm, sort of well understood, but we can always be better. You've got technologies like dissolved air flotation that have worked successfully in a few cases, 10 to 20 cases, have been tried on 10 to 20 cases and have not worked successfully. And so, it's still kind of earlier in that technology transfer commercialization range. And so start to understand and ask questions as you look at manure treatment about, is this commercially tried, tested, well understood? Or are we innovating and pushing the edge of kind of the next phase of technologies, and go into those discussions eyes wide open. And so you've got to do a lot of background work. When we look at our products and values, again, this is very dated. This is from 6 years ago, 7 years ago now, from Innovation Center for Dairy. But it's a reminder that there is value in manure, whether it's greenhouse gases or fiber or phosphorus or nitrogen. Each of these different categories potentially has value to somebody. And some of them are harder to extract, and we can extract value or have not. But there is value in manure. But we got to unlock that potential, in manure treatment technologies begin to allow us to unlock the value in some of these categories. Now, of course, times change. Renewable energy certificates, they're not really RECs anymore, or greenhouse gases at the top there. What was a small bar in 2013 when this was published, that little black line across there, today would make up almost half of this bar graph. And so over time, the values change. Greenhouse gases become valuable. Renewable energy becomes valuable. Electricity becomes not so valuable, but renewable natural gas, which is even on here, becomes extremely valuable. So again, you know, if we would have looked at this in 2012 and said what's going to look like in 10 years, we probably would not have expected renewable natural gas to be a high value product, but it is. And so even though I say you got to use a crystal ball, the crystal ball isn't always right, but it does at least calibrate us and allow us to kind of speculate as to how we manage our systems. Products and markets, again, you know, bedding is a very common item that's used where we take in dry digest manure to make fiber, or just separate a green fiber from an untreated manure. We may dry it, we may use it wet, but manure solids as a bedding is used, and it's a big value saver because it's a recycled product. It doesn't cost us a lot to make it, and it avoids us having to buy it. Compost is a product that, you know, is in high demand this time of year, and so we're able to sell, you know, or the industry of compost is looking for material, selling material at a high rate. It's a seasonal market. There's not, you know, in Michigan in December, not very much demand for compost, at least spot market available that day. So, you know, there's seasonality and flux to these. Manure solids bedding, we're going to use that every day of the year. Work has been done, some at Michigan State with extension, some at University of Minnesota and elsewhere across the country, about converting manure into construction material. So can we make composite boards and decking boards out of, you know, pressed treated manure products? And so a lot of interest in creating innovative and new products and new value, but it is challenging. The Europeans, you know, especially those in the Netherlands and Belgium, have aggressively processed and dried and condensed manures so that they can actually put it on a boat and ship it to parts of the world that are nutrient deficient. So they can take livestock manures and poultry manures from the Netherlands and Belgium, dry it down, put it in a super sack, put it in a 100-pound bag, fill a shipping container, and then they can deploy that nutrient to all parts of the world that are looking for low cost, low value nutrients. And so, you know, a little bit different political, social situation in Western Europe, but again, a good example of, you know, a creative solution in a way to extract some value from the product. Now, the farms pay for the service, and so maybe the farms don't see the full benefit of it, but it allows them to comply with their nutrient requirement regulations and manage their nutrients in a way that is suitable for the different governments and regulatory agencies there. So, but it's being done today. It's been done successfully for a number of years in those areas to export nutrients across the world. When we look at nutrient recovery systems, I work in kind of blocks and arrows and need to have things laid out visually. And so nutrient recovery systems to me are very systematic in that they're going to go in series from left to right on how we evaluate it. We've got a bunch of arrows that allow us to progress and show us products. We also have recycles that are created. So QR is a recycle loop. So we can send processed water back to the dairy for a purpose. And again, the first step in the box is coarse solids, which is very commonly done across the US. It's done to make bedding products. It's done to reduce solids loading to lagoons to avoid crust formation. It's done to clean up flush water or sand separation water to get it to a point where it's of high enough quality that we can use it to dilute and treat manure a little bit. So this box is very commonly done, pretty well understood, and serves a lot of purposes. As we move to the right, we start to begin to move into newer and more innovative and more costly technologies. And so fine solid liquid separation is the next kind of sequential step in the process. This is where we begin to look at removing some nutrients, phosphorus primarily, and we continue to remove solids from the manure stream. Moving further, we're looking at nitrogen recovery, where we're creating a product that's some sort of end concentrate and getting us to, you know, a lower nutrient water, maybe something that's easier to land apply throughout the growing season and gives us a little bit more room in our timing of manure application. It also gives us a higher quality water that we're returning to the dairy, because now we have very little nitrogen or ammonia left in that water, very little solids. And so it's a different quality recycled water that we're sending back, and it may be used for different purposes. All the way to the far right, we get really down to creating clean water or processed water. You know, we've removed the salts from the system. And so really you've got maybe not potable water, but the next closest thing to potable water coming out of this system. And it gives us tremendous flexibility in how we use it on fields. Gives us extremely high quality water to send back to the dairy for a variety of recycle purposes. But we can't go to salt recovery without really doing all the 3 steps in front of it. We can't jump straight to nutrient or nitrogen recovery without doing coarse and fine solid separation. And so we've got to move through this in a sequence, and we've got to realize that every step of the process is dependent on the prior step, and in how that prior step is deployed or used impacts how the next step works and what it can be. So we'll start with coarse solid liquid separation. Really our products here are a fiber product, and then a liquid manure, again, depending on where we fall, because again, realize every one of these technologies has a range in which they operate. They don't all give you one exact product. They give you a range of products, a range of coarse fiber, volume, moisture content, solids recovery. So everything in here is going to work over a range. And again, you've got a lot of different arrows in the quiver when it comes to what goes into each of these boxes. So coarse solid liquid separation has a number of technologies that can be put into that box. Why do we do it? Well, we want to reduce sludge accumulation. We want to reduce crusting. We want to reduce problems with plugging. We want to have easier application. We want to have better quality water for diluting manure that has sand in it for sand separation purposes. We want to send water back to the barn for flushing, and we just want it to have less scum buildup potential, a variety of reasons, and they're not all listed there. But it's, you know, this is the whys. The solids, we use them for bedding. We use them for just a fertilizer, a soil amendment. We use them for compost. And again, technologies that fall into this box, you know, they take all sorts of different shapes and I always lose the laser pointer. Shapes and styles. I mean, there's passive weeping wall systems, there's mechanical systems of different ilk. And so there are a variety of things that fit into the box. Target for total solids separation in this is going to be solids that are in the 700 to 1500 micron range. So again, 0.3 to 0.6 inches or larger would be kind of the range for coarse solid separation. So again, it's undigested corn silage on down to some finer solids components. Again, there is a kind of a bottom range. The technologies, again, they operate in an efficiency of 10 to 25%. That's for one piece of equipment. If I took and put 2 coarse solid liquid separators that operated in series and stacked them up, I might be able to get 35 to 40% total solids, but it's not one, you know, I've put 2 pieces of the same equipment in series and maybe changed, maybe one screw press has a 750 micron screen and the next one has a 1500 micron screen, or vice versa. And so I'm sequentially getting a finer product removed, and I can bump the efficiency above the top end of this range. But realize, you know, if it's a side hill screen, screw press, rotary drum, there are differences, there are ranges in how you operate them. That range will also be driven by what the quality of the product, the solids product that you want. Again, if I want a drier fiber, I may sacrifice some efficiency in some removal of total solids. It's really easy to get 10 to 20% dry matter solids. Again, you can get higher, but there's changes in the equipment that may be required. You may have limitations in the equipment. There may be higher capital costs, maybe higher operating costs. These are kind of the normal ranges where a lot of technologies plug into coarse solid separation. The nutrient separation, it's not a lot here, but it does tend to follow the solids separation efficiency. So if I'm going to get a 10 to 25% removal in total solids, I could probably assume I'm going to get roughly the same on phosphorus and nitrogen. The nitrogen would be primarily organic nitrogen, so the nitrogen that's bound or fixed into those solids. but it's going to be roughly in that range of 10 to 25% as well. If somebody comes in and says, I can put a rotary drum thickener on and I can guarantee you 50% phosphorus removal, probably a reason to ask questions there, because it's probably not able to get 50% of the total solids out. Again, technologies here are numerous, and they take all different shapes and forms, from passive systems, that are static and constructed like settling basins, to slope screens that have no moving parts except the pump that feeds them, to all sorts of kind of moving parts, to really kind of higher efficiency equipment and technologies that may actually start to cross from coarse to fine separation. So again, an array of technologies. You're going to hear me say this a couple of times. The images here are from the nutrient catalog. The website will be at the end of this presentation. A good resource that's been developed by a number of people from the industry that look at this from a technological standpoint, but a wealth of information if you want to get into a better understanding of what a slope screen is versus a screw press versus a rotary drum. Any of these technologies that I'm going to talk about today, they're all discussed, and there's vendors listed there, as well as some reviews of those vendors. So again, use the nutrient catalog that's available. It's publicly available, and it's a great resource for manure treatment technology reference. Again, this is a study. It's a little bit dated, but I think, again, the order of magnitude or kind of the trends here are still reasonable. When we look at primary and secondary, as it's referred to, separation here, again, we see a nutrient separation performance, an approximate OPEX or operating cost range. So again, it's relatively inexpensive, 60 to 80 cents a 1,000 gallons. And relatively inexpensive to install. So an install price of, $4 to $4.50 to $5 for every 1,000 gallon processing capacity. And so, again, the ratios of this technology versus kind of the fine solids are what I'd like to look at here and highlight. And it's not so much the exact numbers, but again, also kind of driving home the point that there are a range to cost, there are a range to performance efficiencies. The next step in the process would be fine solids separation, and that again would stack on after coarse solid separation. And this is where we, as I said, we start to really look at maybe we're targeting some phosphorus separation, or we really want to get to a really low nutrient filtrate or effluent or tea water, as some would call it, that I can spray irrigate, and with a little dilution water, a little fresh water, I could spray irrigate it on a standing corn crop and not worry about harming the plant, covering it with solids, crusting it, caking it, plugging my outlets. So the reasons we go here begin to vary, but there's a lot of, I guess, needs that could justify this expansion of the manure treatment system. So why? Maybe I'm phosphorus limited. Maybe I want less truck traffic. Maybe I want to be able to have a little bit more distance from the fields, or I want to pump to the fields. Irrigation is a big driver here. And maybe I'm in a market where I could sell some phosphorus and some carbon. And I can extract a better value by having more phosphorus in that carbon. And so a lot of drivers, again, the technologies here begin to look different. We've got settlers, we've got dissolved air flotation, we've got belt presses, we've got centrifuges. The technology starts to take a little bit different look and different shape. The uses of the fiber or the solids, again, not so much bedding here, but we start to really move into the fertilizer and compost products, the value adds that would move off farm and allow us to export phosphorus. Those are the drivers that would really, we don't need this step to make bedding for animals, and the bedding is going to have different characteristics because of the fineness of the particles, and maybe also the way we get there. So here we start to really target finer solids. We're going down 2 orders of magnitude, 3 orders of magnitude from where we were at on the prior step. So we get to material that is treated and looks very different. Even though it's still manure, this doesn't look like something that came off the end of a screw press. And so we start to drive to different needs here. These technologies can go, easily 70% phosphorus separation or greater. So, I would say base is 50. Most technologies will get you 70% of the phosphorus out of the water and into a solid stackable material or a very concentrated slurry that can be handled differently. And so we start to change that a lot. Technologies, again, sequential separation. So I could stack some of those coarse separators and design them differently, and I could get maybe to 50%. I can use centrifuges and clarifiers. I can use chemical addition. So maybe I have a centrifuge and I'm able to get 50% phosphorus removal without any kind of chemical addition. But if I add a polymer, now I can get to 70, 75% phosphorus separation or greater. With dissolved air flotation and belt press, we can push that even higher yet. And so the technologies here really start to change shape and form. And we have a wide range at which they can operate depending on what our goals are. Again, lots of technologies here. Some have been tried and used more than others. Centrifuges are probably one of the most commonly used technologies here on dairies across the country, but vibratory screens, belt presses, moving disc presses have all been deployed on multiple farms. Plate presses and struvite and dissolved air flotation, maybe to a lesser extent, but those technologies have been used at commercial scale for this purpose. This is just to give you an example of kind of what this technology can do. This is on a dairy farm that's been using a chemical and belt press system, and you can see total solids on the input, total solids on the output, going from 4% to 0.4% solids. So real significant reduction. Good reduction in total nitrogen, not really much of a reduction in ammonia, huge reduction in phosphorus. And this is probably an extreme case, but it gives you an idea that you can see 90+% removal of phosphorus from the liquid side using technologies like this. Again, looking at it from potassium, not a significant change. And so, as we use the effluent off of this, as we use the product, we still need to make sure that we're thinking about nitrogen and potassium on our fields and how we apply it and what that means for the forages or the crops coming off those fields. Ultrafiltration, or UF, is another technology that is sometimes put into the space. This is from a different farm, but again, an effluent, less than 1% solids, a lot of ammonia or a lot of nitrogen still in that system. Again, primarily ammonia here. A relatively low level of phosphorus, something that you're not going to oversaturate soils applying phosphorus. Applying ultrafiltration filtrate, you're gonna have to apply a tremendous amount to even meet crop utilization needs. But again, a high level of potassium still remaining. So the products have nutrient value. We do need to think about what that is and how we use that and factor that into the growing crop side of it. But real significant reductions in phosphorus with this step of technology, and highlighting that area. And again, this is also highlighting, I guess, two other things that are occurring here. This is a chemical process where we're adding a polymer and maybe some sort of salt product or some sort of ion to separate out dissolved phosphorus. Ultrafiltration uses electricity or energy to run through really fine membranes. And so, there's physical and there's chemical changes that may occur and differentiate how these technologies are. And so it's not a one size fits all by any means. Here, again, thinking back to coarse solids. In coarse solids, this category was under $1 a thousand gallons. Here we're at roughly $3 to $10 per thousand gallons. This cost was $4 to $5 for install per thousand gallons treated a year. Here we're at $8 to as high as $20. And so there's a shift in cost, and there's a shift in operating cost or annual cost. Significant changes in the performance when it comes to nitrogen and phosphorus. So we have moved the bar significantly by adding one more component to the system in what our products look like and what the value means and what the impact is on our manure products. Nutrient recovery, the next step would be nitrogen. So here we're looking at really bringing out that ammonia or pulling that ammonia out of the system, typically in some sort of concentrate. But you can start, if you just step back a little bit here now and start to think about this from a functional operational setting. By the time I go to this step, I have 4 products that I have to manage. I've got a fiber, I've got another concentrated fiber. Maybe these 2 get put into the same pile. Maybe they're 2 different piles. Now I'm adding on a 3rd material. This could be a solid, this could be a slurry. But there's a 3rd product here now that has different composition than the other ones. So how am I storing these? How am I going to utilize these on my farm? And then I've got this effluent. So I still have a product that is still considered CAFO waste or manure. And I have to store this and treat it kind of from a storage standpoint, the same as if it was coming right out of the barn. So while we're doing great things, we need to think about this holistically and say, how do all of these end up properly being stored and then properly being utilized to their best of their value? But nitrogen recovery, primarily ammonia recovery is the next step in the process. Maybe there's application restrictions to the why, maybe again, it's a desire to irrigate more. So if I can get the ammonia out, reduce it now, that's another nutrient that might be limiting on the soil, might be limiting to plant. And now I'm applying more as just strictly a pure irrigation water and not so much for fertilization. There might be a nutrient opportunity. So again, there may be a market for an ammonia concentrate, in different parts of the country. And so there may be drivers for it. Technologies that have been used here in again, not as common as the prior 2 steps, fine and coarse solid separation, but still have been deployed. Air stripping has been used on farms. Very sensitive to temperature, pH, and ammonia concentration of the product going into it. Biological conversion has been used as a way to remove ammonia. Aeration, just driving into the atmosphere, denitrification is another technology or approach that's been done, and that falls under the biological. So, not as many technologies in this category, but different. We've got chemical, we got mechanical, we got biological still there. Products, we could produce just nitrogen gas and just send N2 to the atmosphere, or we could produce a fertilizer product. But we're also then driving to that low nutrient concentration water that now I can apply and use differently. And maybe I'm using it more just as a purely irrigation water. Again, nutrient technology catalog, tremendous resource to read up and get more background on what nitrification, denitrification means, what ammonia stripping means, but also to get an idea of how many vendors and who are the vendors in this space, in what are their on-farm projects, because we're starting to move more into the less commercial systems available. So we need to ask more questions and be more informed when we make decisions in this space. Operating costs now, we're in this $14 to $20 category. So we've gone up in our costs. We've gone up significantly in our cost to install compared to fine solids that were, $10 to $20. Now we're 60 to 90. So the complexity, the level of sophistication and controls drives the price up. Again, and also fewer in the marketplace. And so there's less competition. Significant improvement in nitrogen removal from the liquid side. So we start to see that start to catch up with where we know total phosphorus would be at this point in the system. The last step in the process is really driving to this water. So we either want to produce a high quality water that can be recycled in a lot of different ways on the farm, or we want to produce a discharge quality water that we can then send to a waterway of the United States and meet the same requirements as a municipality would be. So this is really where we start to look at this system as full wastewater treatment on farm, similar to what cities do all across the country. Membrane technology is really an essential process for this. And at this point, we're starting to really move into the final one here on the list, this reverse osmosis. Ultrafiltration, this top red box was actually used for fine solids removal. And so again, when you look at in the membrane area, we've got 4 kind of steps: micro, ultra, nano, and reverse osmosis. This was used for fine solids. Now this kind of same category of technology is coming back in to make high quality water. And you can see the only thing that really passes RO is water, where ultrafiltration allowed different ions to pass through that membrane. But this is really where we start to see technology evolve, and we take steps. And again, that helps us to understand why this is so much more complex and costly. Again, this is a nice little figure that shows, you know, what's getting removed at these different levels, whether it's suspended solids, bacteria, viruses, and then what's passing. And so the tighter that membrane becomes down to reverse osmosis, the fewer things to the point where the only thing that gets through is water. Again, catalog has a really nice description of membrane systems. This has been done a handful of times across the country, and a few farms have actually gone to full discharging of water. They may not discharge regularly, but they have been at least through the permitting process and allowed to discharge at some point. Here, now we're really talking about going from irrigating a brown water to something that a neighbor drives by and doesn't even realize that what you're irrigating is actually, you know, a product of manure. In some cases, this water actually is good enough quality that it can be recycled as drinking water or other really high quality processed water at the dairy farm. And so we're starting to really look at closing the loop, the water loop in this case. We're not only addressing nutrients, but we're also potentially reducing freshwater requirements of a dairy farm. And so this is really pushing out there. By the time we get to this point, you know, we can start to get characteristics and quality and control over the system, so we can really start to look at advanced systems. In this case, dairy in Arizona, growing algae on manure. And so they're able to extract these out, get the water that they need for algae production, feed back in the right amount of nitrogen and phosphorus from the prior steps in the process to create an enriched material that really allows algal growth or other biological growth for value added. So this is an experimental case, but it demonstrates, you know, the control and kind of the process value this could add. You know, we're really pushing 100% phosphorus and nitrogen here. We leave a range there because again, systems can not perform as well every day. Costs have jumped up though significantly. Now we're in the hundreds of dollars a year for operating and capital. And so again, getting to this level of sophistication, you know, requires additional costs from a capital and operating standpoint. So circling back again, you know, nutrient management, manure processing is a sequential process. So we have to really move, and we have to continually look at, we're going to remove the big pieces first. And now we're going to remove the next kind of smaller piece, which is the new big piece. Now we're going to start to remove dissolved materials. And eventually we're going to try and remove all of the dissolved materials in the manure stream. So it is a sequential, it is a systems-based approach. But we really need to keep in mind what all of these components are. Anaerobic digestion does plug in here, and it really plugs in at the front end of the system. So right out of the barn, you know, either right between the barn and core separation, or maybe in some cases it would plug in here immediately following core solid liquid separation, but it could fall into the nutrient recovery, nutrient processing system. The benefits: one, we get some production of gas or energy. We get these emissions controls. We do get a reduction in the organic solids. So there's probably a 30 to 50% reduction in the organic load. So there's a little bit of a reduction in the total solids going in. Manure viscosity has changed because, again, manure that comes out of a cow is very sticky and very viscous because of the mucus that's in there. As we start to dissolve and degrade that during digestion, the viscosity starts to become thinner, or it becomes more flowable or more like water. So there are some efficiencies and some value that goes into the rheological properties of manure. There's an increase in inorganic nutrients. So again, most of these technologies are looking at removing the inorganic forms. And so if we can get more nitrogen in the ammonia form, it's easier to remove in that step. Phosphorus, more of it that is in that inorganic form may be able to reused or separated better in that fine solid step. Again, when you look at our climate, our manure temperature is going to be the same now every day of the year. So it's not going to go from 70 degrees today to 30 degrees or less in January. Coming out of a digester, it's always going to be relatively the same temperature. That adds ease to the whole processing standpoint. It's also uniform. I don't have to worry about, is it dry cow manure now that's coming through the manure system? Is it fresh or high lactating cows? There are small chemical composition changes in manure. Now it's all uniform and it's consistent. Again, the myths, volume is going to be the same coming out of a digester. Nutrients, the load is going to be the same. Those aren't changing. And so we can't really account for reductions in those as we start to plan and think out a system. Again, think about what your cost of manure application are today. This is, again, a little bit dated out of University of Idaho, but it looks at knife injection to knife drag line, using nurse tanks, doing direct pump. I apologize. Now, this is cost per gallon, not cubic meter. So I need to fix that. But, get a handle. Are you spending a penny a gallon? Are you spending 2 cents a gallon to land apply manure? What is your current cost? What does it cost per cow? And again, can I improve and spend a little bit money on this step to do a better job, with my nutrient management to reduce the odors so that my neighbors don't notice me as much, to take truck traffic off the road? Is this a better, spend of money here? And is it more cost effective to do this? Or is it more cost effective and long-term better to go into that complete manure treatment system? So how you apply and what your costs are associated with land application of manure should drive this conversation and should be part of the factors that go into it. Again, this is a resource that was developed out of the dairy industry. I have served as a technology advisor to Nutrien, as along with a number of my colleagues from across the country for a few years. This is a great resource. It's there. It's a catalog of not only the equipment types, but also vendors. And it talks about the vendor's experience with on-farm projects. So this is really moving away from the research and the testing side of it. And this is looking at technologies that are vetted and have been used on farms and that are commercially viable, commercially ready. And so again, take advantage of this. It's there. And it's a nice starting spot to get yourself informed about what technologies are out there and available. So where do we stand today? Well, I mean, manure application costs are really still relatively inexpensive. And so again, do we spend a little bit more on that end of the system to improve some of our concern areas and maybe address some of those needs? And we need to weigh that when we look at adapting and spending technology or spending money on infrastructure and technology. Social pressure is extremely high. It's only getting higher, and that, we see that with changing regulations here in the state of Michigan. There's been a ramping up of the requirements of how we manage and apply and use our manure. And that's not going to change. It's in the focal point, and it's going to only increase as time goes on. Nutrient technologies, to some extent, a lot are still in the early adopter phase, but a lot are also, commercially viable and tested. And again, when you start with Coarse and you move to the right, the farther you get, really kind of the farther you are probably into the early adapter phase. So commercially viable technologies are available. Capital costs and operation costs are variable, again, depending on where you're at in that continuum. But do know that they are relatively higher. And again, they can get extremely high if you go to really high quality processed water that's produced. Nutrients don't go away. They still require management. As I highlighted here, they're still considered CAFO waste. They still require storage and handling as if they were raw manure. And so we have to have a plan for how we're going to use those nutrients. And we need to understand how they're going to be stored and then what the right timing and utilization method is for those products. Again, consider your storage side of it. Plan for those nutrient products. In the future, storage design standards may change. And if we start to see more water with less solids in it, that has different storage requirements, or could have different storage requirements than what we do with what we normally see as just raw manure, untreated manure. And so keep in mind that, again, some of these things, while they still are categorized as CAFO waste here in Michigan, over time that may change because their characteristics are different, and the storage requirements may change with that. Resources and opportunities do exist. The technologies are there. As I indicated, nutrients are a great resource. MSU Extension, Cornell, a number of other universities across the state have, or across the country have, a lot of resources available. Use those, get some unbiased opinions and some thoughts on it, and then reach out to the vendors and get some additional information and start to work through it. But again, realize there is a tremendous wealth of information available to you today to start you thinking and start to get some clarity around the topic area. With that, I think I've used about my hour.
Thanks very much, Dana. Spectacular. So one question, if I understood one of your first graphs correctly, in the Great Lakes watershed area, about 3/4 of the fertilizer that's applied to crop ground is still commercial fertilizer, inorganic, if I'm saying that right. Is that correct?
Yeah, that's based on the work that's been done by EPA, Ohio EPA, others in the region here. Correct. The majority of the fertilizer application in this basin is from commercial sources, not manure sources.
Okay, so if we want to see that as an opportunity for dairies to sort of capture a market, if they do invest in a more expensive manure treatment operation, is there a additional agronomic value to phosphorus from these recovery systems? Is it more available to crops? Is it more likely to stay in the soil as opposed to leaching?
Yeah, and I think that's a great question, and it's a great opportunity and challenge. I mean, phosphorus is phosphorus. It comes in all sorts of different forms, but at the end of the day, it is phosphorus. It might be phosphate or superphosphate, or it will have different characteristics and it will react differently in the soil. So organically bound nitrogen or organically bound phosphorus in manure, it takes time for that to degrade and become available. And so when we look at just applying raw manure, a certain percentage would be available the first year to the crop. A little bit more is available the second year. A little bit more is available in the third year. Some of these would increase that inorganic component that's available day one. Some of these technologies would increase the carbon content that's associated with that phosphorus. So there's a variety of value that's added, and it needs to be communicated out to the row crop or the cash crop farms to, say that manure really does bring value. The nitrogen and phosphorus and potassium and other micronutrients and trace minerals that are contained in manure, as well as the carbon, have great value to soil health and productivity. But we need to communicate that better. We need to talk about what to expect when you use manure or manure products on soil, and that it's not going to react the same way as a commercial fertilizer might. But there are long-term benefits, and we probably need to do some really good studying and demonstration of how that could be done. With a multi-year demonstration to say this is what manure can do to soil over 3 or 4 years of continuous and proper use, and ideally the benefits would be great.
Okay, great, thank you. That helps a lot. Dana, excellent job again. Thank you very much. You laid things out very clearly, and I appreciate your time. So with that, we'll wrap it up for today. Again, thanks to Dr. Dana Kirk for joining us, and I hope you found value in that. Have a good day.